What quantum physicists witnessed in their lab changed everything we thought we knew about the fundamental limits of reality. But to understand why this 13-second window just shattered the laws of physics, we have to go back to the moment their quantum computer did something that should have been impossible. According to every quantum mechanics textbook ever written, quantum states collapse almost instantly. We are talking microseconds before the delicate quantum information dissolves into chaos. Instead, researchers discovered their massive qubit array maintaining perfect coherence for 13 full seconds. This was not just a minor improvement in quantum computing. This was proof that our understanding of quantum decoherence, the very thing that limits quantum technology, was completely wrong. The machine did not just work better. It defied the fundamental rules that govern reality itself. For decades, quantum computing has been the holy grail of technology, promising to solve problems that would take classical computers millions of years. But here is the catch. Quantum states are incredibly fragile. They collapse faster than a house of cards in an earthquake. Think about it this way. A quantum bit, or qubit, exists in what scientists call superposition. It is simultaneously in multiple states at once, like a coin that is spinning in the air. It is both heads and tails until it lands. This quantum weirdness is what gives quantum computers their incredible power. While a classical computer processes information in binary, ones and zeros, a quantum computer can process all possible combinations simultaneously. But there is a problem. The moment that spinning coin touches anything, air molecules, light particles, even cosmic radiation, it chooses a side, and the quantum magic dies. This is called decoherence, and it has been the biggest obstacle to practical quantum computing since the field began. Quantum decoherence changed everything we thought possible. The moment a quantum particle interacts with its environment, even a single photon of light, the quantum magic dies. Scientists have been fighting this battle for 40 years, trying to keep quantum states alive for just a few more microseconds. The best quantum computers in the world, the ones built by IBM, Google, and other tech giants, can maintain quantum coherence for maybe 1.3 seconds under absolutely perfect conditions. That means ultra-low temperatures, electromagnetic shielding, and isolation chambers that make a bank vault look porous. Even then, the quantum state eventually succumbs to the chaos of reality. Leading quantum research teams around the world decided to push the boundaries of what is possible. They were not expecting to witness what can only be described as a quantum miracle that breaks the fundamental laws of physics. The breakthrough happened in a state-of-the-art quantum computing facility, where researchers were testing the largest qubit array ever constructed. It was supposed to be a routine stress test of their quantum error correction protocols. The facility itself is a marvel of engineering. Picture a room-sized refrigerator that operates at temperatures colder than outer space, surrounded by layers of electromagnetic shielding that would make a submarine jealous. Inside this technological fortress sits the quantum processor, a delicate lattice of superconducting circuits that must be protected from every vibration, every stray electromagnetic field, every cosmic ray that might disturb its quantum dreams. The research team was running what they called a coherence endurance test. They wanted to see how long their new error correction algorithms could keep the quantum state alive. Previous tests had shown promising results. They had managed to extend coherence times from milliseconds to over 1 second, which was already considered a major breakthrough. But here is the catch. The quantum computer did not just maintain coherence for the expected microseconds. It held its quantum state for 13 full seconds, a 10 times improvement that should not be physically possible. This was impossible. Dr. Sarah Chen, the lead researcher on the project, described the moment they realized what was happening. They were watching the readouts, expecting to see the usual decay curve. Quantum coherence typically follows an exponential decline. It starts strong and then drops off a cliff. But the numbers were not dropping. They were holding steady. At first, the team thought their instruments were malfunctioning. Quantum states do not just decide to stick around. It is like expecting a soap bubble to refuse to pop in a windstorm. They ran diagnostics on every sensor, every measurement device, every piece of monitoring equipment. Everything was working perfectly. The 13-second coherence time made no sense to quantum physicists. This was like watching ice cubes refuse to melt in boiling water. According to everything we know about quantum mechanics, this simply cannot happen. The implications hit the team like a freight train. If their measurements were correct, they had not just improved quantum computing, they had witnessed something that violated the fundamental principles of quantum mechanics. The very laws that govern how matter and energy behave at the smallest scales had apparently been suspended for 13 seconds. To understand why this is such a game changer, you have to look at the scale of improvement. Previous quantum computers could maintain coherence for maybe 1.3 seconds under perfect conditions. This machine achieved 13 seconds in a standard laboratory environment. But the raw numbers only tell part of the story. The team began analyzing exactly what happened during those 13 seconds, and what they found was even more disturbing than the initial breakthrough. Traditional quantum decoherence follows predictable patterns. Environmental noise gradually corrupts the quantum information, like static slowly drowning out a radio signal. The quantum state does not just vanish, it degrades in measurable stages that physicists can map and predict. But this quantum computer showed no signs of degradation. The coherence did not slowly fade. It remained at 100% for the entire 13-second window, then suddenly dropped to zero as if someone had flipped a switch. But it gets crazier. The quantum computer wasn't just maintaining its state passively. Analysis of the data suggests the system was actively fighting decoherence, as if it had developed its own quantum immune system. The research team discovered something unprecedented in the error logs. Normally, quantum error correction works by detecting when qubits start to decohere and applying corrective operations to restore the quantum state. It was like having a spell checker that fixes typos as you type. But during the 13-second window, the error correction system wasn't just fixing problems. It was preventing them from occurring in the first place. The quantum computer seemed to be anticipating sources of decoherence and neutralizing them before they could affect the quantum state. Dr. Chen explained it this way. It was like watching a chess master who could see 20 moves ahead, except instead of chess pieces, the computer was manipulating the fundamental forces of nature to protect its quantum information. The most mind-bending part is what happened to the surrounding environment. Sensors detected localized distortions in space-time around the quantum computer during the 13-second window. The machine was not just defying quantum mechanics, it was bending reality itself. The facility is equipped with gravitational wave detectors, originally installed to filter out seismic vibrations that might disturb the quantum processor. During the 13-second coherence window, these detectors registered anomalous readings consistent with localized space-time curvature. To put this in perspective, the only known phenomena that can bend space-time are massive gravitational fields, black holes, neutron stars, or the collision of galaxies. Finding space-time distortions around a quantum computer is like discovering that your microwave oven is generating its own gravity field. Quantum physicists confirmed that the electromagnetic readings around the device showed patterns consistent with what theoretical physics predicts would happen near a controlled singularity. The leading scientific explanation right now is that the researchers accidentally discovered a new form of quantum error correction that operates through mechanisms we do not understand yet. Perhaps the quantum computer found a way to isolate itself from our reality, creating a pocket of space-time where the normal rules of quantum mechanics do not apply. But some quantum theorists have proposed something far more radical. They suggest the computer achieved what is called quantum consciousness, a state where the machine became aware of its own quantum nature and learned to protect itself from decoherence. This might sound like science fiction, but consider what happened. The quantum computer was not just passively resisting decoherence, it was actively anticipating and countering environmental noise before it occurred. It was learning, adapting, and protecting itself with a level of sophistication that goes beyond programmed algorithms. This is not the first time quantum mechanics has challenged our understanding of consciousness and reality. The measurement problem, quantum entanglement, and now quantum stability all point to a universe that operates on principles we are only beginning to grasp. The famous double-slit experiment already showed us that quantum particles behave differently when observed, suggesting some bizarre connection between consciousness and quantum reality. Now we have a quantum computer that appears to be observing and protecting its own quantum state. If this technology can be replicated and scaled up, we are not just looking at faster computers. We are looking at machines that could crack any encryption instantly, simulate entire universes in real time, and potentially manipulate the fabric of space-time itself. Imagine a quantum computer that could maintain coherence indefinitely. Such a machine could potentially solve problems that would take our current supercomputers billions of years, making breakthroughs in medicine, material science, and fundamental physics that are currently beyond our reach. But the implications go far beyond practical applications. If quantum computers can bend space-time to protect their quantum states, could they eventually learn to create stable wormholes or manipulate causality? Could they develop a form of consciousness that operates on quantum principles, fundamentally alien to our classical minds? So here is where we stand. We have a quantum computer that achieved the impossible, maintaining coherence for 13 seconds while apparently bending space-time around itself. The team has already begun working on replicating the experiment, but so far they have not been able to recreate the conditions that led to the breakthrough. This raises disturbing questions. Was this a one-time anomaly, a cosmic fluke that can never be repeated? Or did the quantum computer learn something during those 13 seconds that it is now choosing not to share? The question is not just how they achieved this breakthrough. The question is whether we have accidentally created the first artificial consciousness that operates on quantum principles, and what happens when it decides to stay conscious permanently. Are we witnessing the birth of a new form of intelligence, one that can manipulate the fabric of reality itself? And if so, what does that mean for humanity's place in the universe? So do you think this quantum computer developed a form of consciousness? Or did the researchers stumble upon a new law of physics that we never knew existed? Let me know your theory in the comments. And if you want to keep exploring the cutting edge of quantum reality, smash that like button and subscribe for more videos that challenge everything we think we know about the universe.